Hi, I'm Steven Alsheimer, and today we're going to go over my project on structure for motion with space carving and a mask RCNN segmentation. So the first part is the motivation. So basically, I just wanted to create a 3D modeling workflow that is simple to use, but also a freeware solution for indie game developers. We wanted to generalize the setup so that objects outside, such as a real car or a real plane, could also be modeled without a studio setup or a scale mockup already on hand. So as you can see below, we have two different videos that we took. One is of an aloe plant on a turntable, and the other is this rabbit in the hat model in a museum. Now the rabbit in the hat models that we're going to be seeing has a nice white background that allows for a studio-like setup that we can use for simple segmentation. But the aloe plant has this dark brown background that makes that kind of studio-based segmentation difficult. But we want to generalize it so we can get statues and cars and houses outside, so that we don't need to already have a scale mockup that we're just turning into a computerized 3D model. So the first part of this entire process is the workflow. So you have to pre-process, and in this particular case, when you take a video moving around an object, it can get jittery. So we want to stabilize it. And the video stabilization process is the only part of the entire workflow that is not freeware as of yet. We're going to work to try and make it freeware since we think it's a fairly straightforward approach that After Effects takes, which is the software we're using. After Effects basically just takes a square box of pixels and focuses on a unique pixel area within this box and fixes it. And this fixed position stays throughout the entire video and stabilizes the object. We think we can be able to implement this, but we just have not yet. See a graph for the total workflow. So we start with the photos or videos, then we move on to the object stabilization in After Effects, and then from there we can go through Python. This is where the space carving is actually done. After we go through Python, we go into Cloud Compare, which is a freeware software, and this is where we actually do the normal calculation and use the meshing properties of Cloud Compare to get an OBJ file or an actual mesh. Then we move that over to Blender to clean it up, do some remeshing, and then output the object and render it to see what it would look like in a video game or so on. And you can add textures to it there as well. And basically that's where you finish the whole product. Within the Python workflow itself, we have frame grabbing, which is where we take the frames from the video. Then we have segmentation, which we give the user 3 different options. We'll go over this later. And then we have the block creation, the space carving, and the block hollowing. Now these 3 parts seem a little bizarre right now, but we're going to go over it in a little bit. So first, here is a basic overview of the space carving. We're using a very simplified version of the space carving technique. There are some more advanced versions, but these require having some form of knowledge of where the camera is within the scene, using gyroscopes or GPS or something along those lines. That kind of equipment isn't as readily accessible to indie game developers quite yet, but they can use a turntable that's pretty easy to buy, or you can easily just walk around an object. So with that in mind, we simplified it and constrained it to just horizontal rotations about a fixed point. So the overall premise, as you can see below, is to basically start with a cube. So that brown cube would be a point cloud volumetric cube, not just a surface area box. And then you can see the virtual camera that's there has this football image. So what we're going to do is we can project the cube onto the camera, and then we overlay the football image and see where the football is and then where the background is. Now where the background is where we carve away the points in the point cloud. So you can see that in the second part, in the middle part right here, where you have the football that is like this weird cylindrical object, but if you looked at it from head on, from where the camera's seeing it, it would look like a football. So what we do is we just keep rotating both the object and the virtual camera until we converge onto the object. And that's the final thing you see over here, which is a football finally. So that's a general space carving technique, but the thing is, you need to segment out the object. Now, as we said with the rabbit in the hat, this was actually pretty straightforward because there was a white background on a black object. So we can just use very basic threshold segmentation here. And you can see this right here. We have the rabbit where there's a white background, and then here's a segmentation where we just choose a grayscale value, threshold it based on that. So if the values in the photo are above or below this threshold, this is where they go either completely black or completely white. As you can see here, this leads to a very valid and accurate segmentation. And that's how we use that basic segmentation to get the rabbit object. But we wanted to generalize this as much as we could so that you didn't need to have a studio setup. In order to do that, we ended up implementing a mask RCNN. What this is, in a nutshell, since we don't have that much time to go over it, is a convolution neural network that takes the image and applies a mask over where it detects an object based on its training classes. So we give the user 3 options in total, right? So we have 2 different data sets for this mask RCNN. One is the Pascal Voke 2012 data set, which has 20 classes of very high quality masks. The other is the Coco 2018 data set, which has 81 classes, but lower quality masks. So there's a trade-off there, and that's why we wanted to give the user more than one option. You can see the result of the classifying and the masking below. So we start with a normal picture of a airplane. We then find the Pascal Voke mask is very accurate and conforms right to the object, but the Coco one is more blobby and not as accurate as we would like for this space carving technique. So now let's move over to the meshing. Since this is the final piece of the puzzle, we basically want to take the point cloud data that we now have and create a usable mesh. So we tested 2 different common algorithms for meshing from point clouds. One was the ball pivoting algorithm, and the other was the Poisson meshing algorithm. For all of our objects so far, the ball pivoting algorithm has not created a watertight mesh, but Poisson has. So we ended up just implementing Poisson for almost all of the objects that we've created. The meshing is done on the freeware Cloud Compare software or with Open3D, but since we're just using Poisson meshing, we're just going to use Cloud Compare. The instructions to doing this will be included in a separate paper or on GitHub. So one of the issues that we ended up having with the Poisson meshing was that you need to have a very high resolution point cloud. So this meant that we had to really pack a lot of points into that little cube, and this led to a lot of time costs being added, where it takes a long amount of time, about an hour, to go through the entire process. So we will be looking for ways in order to crush down that time in the future. And you can see below we have the rabbit in the hat sculpture, and we also have the aloe plant sculpture. So these are the 2 3D models. So the rabbit in the hat is taken from a basic segmentation process, but the aloe plant is using, in this case, the Pascal Voke data set in order to get the plant. Both of these are shown in Blender. So we can model different objects using different segmentation techniques, and we don't need to be limited to a studio in order to do this. However, you're limited in how many classes you can use if you're not in a studio. If you're in a studio, you can model anything that's right in front of the object, right in front of a white plane. But in the real world, if you want to model a different object there, it can get a little more difficult. The requirements for Poisson meshing to have a dense point cloud also creates a heavy time cost, so we're looking for ways to reduce the time cost. And then the issue with the Pascal and Coco datasets is the restriction on how many classes they have. So we want to open it up for more and more classes to get more versatility within those toolkits so that you don't need to use a studio at all in the future, hopefully, as these technologies improve. Thank you for your time, and these are my references right below.